So now we're working on part C, and we have an LLRB. Part 1 of C is similar to A and B in that we're trying to find the insertion operations to produce this tree. And the key thing for this question is that LLRBs actually have a one-to-one mapping to 2-3 trees. They are also self-balancing and have rotations. So again, no matter what sort of order we insert the 3 nodes, it should always give us this shape since it is self-balancing. So the answers for this question should be the exact same as our answers for the 2-3 tree. So that would be all of these are valid. And we can verify that by running through some of these scenarios. I'm just going to focus on one. And if you want to solidify your understanding of LLRBs, feel free to go through the other ones as well. And you should result in this structure. But let's say we're doing this one. So we're going to first insert our 3, and then we add a 1 here. Now this one is going to be a red node. I'm using the star to denote red nodes, mainly because it's easier to erase and work with right now, instead of like shading it. But that just means it's a red node. And then after that, we're going to insert our 2. It's also a red node. And that's actually a problem because our red node should always be on the left. So we need to rotate this to the left. So we're going to call rotate left on 1. And that's going to give us this spindly tree shape here. And this is also still a problem because we have 2 red nodes in a row, which is again illegal for LLRBs. So now we need to perform a right rotation. And so we're going to rotate right on 3. So it's going to bring our 3 down. And that's going to be red. And now we need to fix this one more time. So we need to fix this to color flip because we have red nodes on either side. So our root's going to be red, but our root should never be red. So, so we're going to change that to black. And so that gives us our ultimate, our final answer over here, 2, 1, 3. For part 2, I'm just going to move this out of the way. For part 2, we want to figure out what's the, oops, sorry. For part 2, we want to figure out what's the minimum number of rotations to achieve this structure. And a good start is to find out what exactly is that minimum, and then see which orderings will achieve that minimum. So the idea here is that it should be very similar to our original, like inserting into a regular binary search tree, because that's going to be most closely or most similar to the final shape. So in other words, we want to pick the ones that insert 2 in the beginning. So let's run through each of these options and see which one is better. So if we insert the 2 first, then we can add in a 1 and then a 3. So we can see here that there were no rotations that need to be done. But if we did the 3 first, now we would have a red node on the right side, so we would need to rotate this to the left, and that would just get kind of messy. So in this case, when we do 2, 1, 3, that actually required 0 rotations. So there's definitely no way that it could be any less than 0. And so, yeah, so this should be our best one. Now for the other options, we can see here that the root is actually 1 or they're not 2 in any of the other scenarios. So it would require at least 1 rotation to fix the root. So what that means is that all of these cannot be the answer because here we have an answer that requires 0 rotations. For part 3, we want to find out which ordering requires the maximum number. And this one is definitely quite tricky. I would say that there isn't really a good way to find a shortcut for this problem. You kind of have to run through all the options. But something that might help is to know the general structures and shapes of LLRBs and how many rotations it takes to fix them. So if we have this kind of scenario over here, this requires at least, or I mean, this requires 2 rotations to fix. So we would need to rotate left, right there. And then after that, we would get sort of a line shape. And so we would need to rotate right again to fix that. So ultimately, that requires 2 rotations to fix. Yeah, so this would become this sort of spindly shape that requires another rotation to fix. So total requires 2 rotations. Yeah, so if we keep this in mind, it might help us make some shortcuts as well. Yeah, we kind of have to just run through all of these. So if we do 1, 2, 3, let's see how this progression will evolve. So first, add in the 1, then the 2. This needs to get rotated left, so that becomes 2, 1. And then we add in the 3 over here, and we're done. So this requires 1 rotation. So I'll just put a 1 right there. For 1, 3, 2, first we're going to add in the 1. Then we're going to add in the 3, and we need to rotate left again. So 3 and a 1, and then we add in 2. And here we can see we have the structure that we were talking about before. So this is going to take 2 rotations to fix. This one required 1 rotation, so 1 plus 2 gives us 3. So this requires 3 rotations. And as we move forward, we can see that we will find out that 3 actually happens to be the maximum. So this is the maximum, but I'll also go through the rest of these. So we definitely know it can't be this one because that was our minimum. But 2, 3, 1. So 2, 3, 1. Let me just clear this again. So 2, 3, 1, we added a 2 and a 3. We need to rotate that to the left. So 3, 2. Oops, sorry. 2, and then we added a 1. So this requires 2 rotations because this structure requires 1 rotation to fix. So this requires 2. When we do 3, 1, 2, that gives us the structure that we were talking about. So this will require 2 rotations to fix. That requires 2. And then when we insert 3, 2, 1, that should give us this structure, which requires 1 rotation to fix. So that's a 1. So we can see here that 3 is indeed the maximum, and this is the only ordering that gives us that 3. So that's it for this question. I hope this was helpful, and I'll see you later. Bye.